Welcome everybody to my e-poster called Incorporating Temporarily Persistent Scatterers into a Multi-Stack PSI Approach to Investigate the Initial Settlement of New Buildings. The persistent scatterer interferometry is a really powerful technique to monitor displacements of the Earth's surface. A major limitation of the technique is that persistent scatterers have to be present during the whole considered time series. Temporarily persistent scatterers, called TPS, which are only present during a period of the considered time series, are not detected and analyzed. In this work we present a method to incorporate appearing TPS into an existing PSI algorithm and apply this method to monitor the initial settlement of new buildings in the Vietnamese city of Cà Mau, which has recently been characterized by high construction activity. We use a multi-stack small baseline PSI approach, which was described in Schenk 2015. The parameters height, linear displacement rate and thermally induced displacement rates are estimated using 3 1D periodograms sequentially instead of using one 3D periodogram in order to reduce the computational cost. In order to tackle the problem of noise propagating into the 1D parameter estimation from the non-estimated parameters, we use two approaches. The first one is to use different small baseline subsets for each of the parameter estimations, and the other one is to use an iterative sequential parameter estimation where only that parameter is reduced from the phase in each iteration step, which increases the coherence the most. Our TPS detection and change point estimation is based on the approach by Ansari et al. 2014, which makes use of the fact that the amplitude of a distributed scatterer is best described by a Rayleigh distribution, while the amplitude time series of a PS follows a Rice distribution. TPS are detected by segmenting the time series into two equal-sized parts and selecting one of the four here described models with highest likelihood. Afterwards, the change point for the identified TPS is estimated by going through every acquisition of the time series, taking this acquisition as a potential segmentation point and choosing in the end the segmentation point with highest likelihood for the given model as change point of the TPS. We found that the estimated change point of appearing TPS by purely analyzing the amplitude time series is sometimes too early. For example, in this case, the start of the construction phase of a building was chosen as change point when the real change point for the PS is the finishing date of the building as seen in the interferometric phase time series. This is why we later refine the change point estimation during the parameter estimation. The procedure of the TPS parameter estimation and change point refinement shown here. We start with the initial change point estimated from the amplitude time series and afterwards estimate the parameters by just introducing a weight into the 1D periodograms, which flags interferograms outside of the TPS lifetime with a 0. After each iteration step of the parameter estimation, the change point of the TPS is re-estimated using a moving coherence. Finally, the selected PS and TPS are jointly unwrapped using a modified version of the 3D unwrapping algorithm implemented in the STEMS software. The unwrapping in STEMS is performed on gridded wrapped faces. We also add the faces of TPS to this gridding operation for interferograms inside their lifetimes. It might be the case that certain grid cells are only occupied by TPS, which all aren't present in certain interferograms. We interpolate these grid cells in the given interferograms by non-empty nearest neighbors for the purpose of incorporating them into the 3D unwrapping. We applied the proposed method to a Sentinel-1 stack covering the Vietnamese city of Cà Mau. Here on the left you see the results of a standard PSI run where no PS were identified in a district which was built during the Sentinel-1 time series stack. On the right you see the results of the PSI algorithm incorporating also TPS. Many TPS are found in this mentioned district. Here you can see the displacement time series of a PS on a street next to the district and of TPS in the white square, which approximately appeared after the 120th acquisition of the time series. We identify a high initial subsidence of ground PS with decreasing subsidence rates, while the building TPS are relatively stable, probably due to the foundation of the building. Thank you very much.